Welcome to the first lesson of the sixth topic, Graphs of Rational Functions. Lesson 6a is all about transformations and limits of rational functions. We'll learn about finding domains of rational functions and transformations of the function 1 over x. We'll also learn about asymptotes and end behavior. I'm Mr. Stark, and this is Polynomial and Rational Functions. Let's get rational. We'll start this lesson by finding the domain of a rational function. We've done this before, but it was in the context of learning about domain and how to find it. So, just in case you forgot, there are two issues when we're finding the domain of a function. Number one, dividing by 0. Number two, taking the even root of a negative number. Since we're talking about rational functions, we're dealing with the first issue. But how do we know that? Well, a rational function is the ratio of two functions. We can say r of x is equal to f of x divided by g of x. That means g of x cannot be equal to 0. Otherwise, we have an issue. Let's apply this to the example. Find the domain of r of x and use limits to describe the behavior at values not in its domain. To find the domain, we set the denominator equal to 0 and solve for x. Therefore, when x is negative 2, r of x is undefined. So x can't be negative 2, and the domain is negative infinity up to negative 2, union negative 2, comma infinity. And we use parentheses to communicate that x can't be negative 2 or infinity. Before we use limits to describe the behavior at x equals negative 2, let's get a feel for what this graph looks like. The function 1 over x is one of the 12 basic functions, and this function r of x is a transformation of that function. There are two transformations, and I hope you could see them. There's a horizontal translation to the left 2 units, and a vertical stretch by a factor of 2. So I'll grab some points from the original function and transform them. Let's start with 1, 1. Shift it left 2 units, then double the y value. Next up, negative 1, negative 1. Shift that left 2 units, and double the y value. Now we could sketch a curve that goes through those 2 points that looks like the original graph. What used to be a vertical asymptote at x equals 0 is now a vertical asymptote at x equals negative 2. Now we could take the left-hand limit and the right-hand limit at x equals negative 2. So we have the limit as x approaches negative 2 from the minus side of r of x, and the limit as x approaches negative 2 from the plus side of r of x. To calculate the limit from the left side, we'll put our pencil as far left as we could go and then follow the curve until we get to x equals negative 2. As x approaches negative 2 from the left side, the y value, or r of x, approaches negative infinity. For the right-hand limit, we'll put our pencil as far right on the curve as we possibly can and follow the curve until x approaches negative 2. So, as x approaches negative 2 from the right side, the y value, r of x, approaches positive infinity. Notice how those two limits describe the behavior of r of x at x equals negative 2. On the left side of negative 2, the y values are getting very negative, and on the right side of negative 2, the y values are getting very positive. Let's continue studying transformations of 1 over x. I personally think what we're about to do is pretty neat. In this example, our rational function is in the form of ax plus b divided by cx plus b, such that a, b, c, and d are real numbers. So identifying the transformations is a little more difficult, but we can use synthetic division to help us. Let's do the example. Describe how the graph of k of x can be obtained by transforming 1 over x. Then sketch k of x. Since 2x plus 4 is being divided by the binomial x plus 3, we can use synthetic division. Negative 3 goes in the box because the 0 of x plus 3 is negative 3. The coefficients are 2 and 4. We'll draw our horizontal line and drop down the 2. 2 times negative 3 is negative 6. Add to get negative 2, and we're done. Negative 2 is the remainder, and positive 2 is the coefficient of x to the 0. So k of x is equal to 2 plus negative 2 divided by x plus 3. Now let's identify the transformations from the inside out. First, we have a translation to the left 3 units. Then we have a vertical stretch by a factor of 2. The negative sign reflects the graph vertically over the x-axis. Finally, the positive 2 translates the graph up 2 units. Now I think we could sketch the function k of x, as long as we start with the original function f of x equals 1 over x. So I'll grab 1 point on the graph, 1, 1. Left 3 units, double the y value to get to 2, flip that over the x-axis to negative 2, and then shift it up 2 units to 0. We can do the same thing with the point negative 1, negative 1. Translate left 3 units, double the y value, multiply the y value by negative 1. Finally, translate up 2 units. There's a vertical asymptote at x equals negative 3 and a horizontal asymptote at y equals 2. The original function 1 over x had a horizontal asymptote at y equals 0, and this function is shifted up 2 units. Now let's see if you could do a few transformations on your own. Your challenge is to sketch graphs and find equations for transformations of 1 over x. There are 2 situations. Each one has multiple transformations. Try them out, and I'll have the answers for you in just a moment. Pause now. Okay, here come the answers. Here are the graphs and the equations. The last 2 concepts that we'll cover are asymptotes and end behavior. One way to find vertical asymptotes is to set the denominator equal to 0 and solve for x. As long as the numerator does not share a factor with the denominator, the resulting equation is the equation of the vertical asymptote. By the way, if they do share a factor, the resulting equation is the location of a hole. Another way to find vertical asymptotes is to use limits like we did above. But that's a little too abstract for what we're doing, and we'd have to find the zeros of the denominator anyways. So let's set x plus 1 equal to 0 and x plus 5 equal to 0 and solve. The vertical asymptotes of this function are x equals negative 1 and x equals negative 5. Horizontal asymptotes are found by taking the limit as x goes to positive infinity and negative infinity. Doing that helps us understand the end behavior of the function when x is very large and when x is very small. So let's take the limit as x approaches infinity of f of x. What is that? Well, if we consider plugging in very large values for x, something like 1,000,000, then it'll help us understand what's actually happening. In the numerator, we get something like 2 times a large number times another large number, divided by 1 times a large number times another large number. The result is basically 2. But if you're not convinced, let's consider x approaching infinity, not just being 1,000,000. As x approaches infinity, adding a 3 or subtracting a 3 barely affects that number at all. Think about it. Infinity is so very large. It's bigger than any number we could say, think, or write. And we want to just add 3 or subtract 3, add 1 or add 5? No. Those numbers are barely going to make a difference. Therefore, we can rewrite this as the limit as x approaches infinity of 2x squared divided by 1x squared. And that can be simplified to 2. That means the equation for the horizontal asymptote of this function is y equals 2. By the way, the shortcut to find the horizontal asymptote for this function is to use the mnemonic Betsy. Since the bottom degree equals the top degree, we divide the coefficients of x. 2 divided by 1 is 2. And that is the first part of Topic 6 of the Polynomial and Rational Functions unit. I'm Mr. Stark. Join me for the next lesson, Lesson 6b. Did you press that subscribe button yet? Give me a thumbs up if you liked the video. If you have a question, you might as well ask it. Do you have a comment? Feel free to add it. Hey, thanks for watching.